All right, so right off the bat here, this 8 grams, you want this to be in kilograms. So the bullet's going to be M1. So 8 grams is 0.008 kilograms, and then the block here is M2. 250 grams is 0.25 kilograms. All right, so look, is there a collision happening in this problem? Yeah. What do you think about when you see a collision? You think, oh, in a collision, whether it's elastic or inelastic, doesn't matter. What's always conserved? Momentum. Momentum is always conserved. Now, this problem is inelastic simply because the problem, it doesn't say elastic, okay? If it's an elastic collision, the problem has to tell you. And it makes sense that it's inelastic because for this sort of collision, if a bullet's going into a block, you're going to lose a bunch of energy because it takes energy to put a hole in the block. All right, so what we're looking for in this problem is V1 initial, the initial velocity of the bullet. And by the way, what's the initial velocity of the block? 0, it's just sitting there. Okay, so we write out conservation of momentum equation, M1 V1 initial plus M2 V2 initial. Oh, what do they tell us in the problem? The bullet remains in the block, right? So the two objects stick. So our final momentum is going to be M1 plus M2 V final. They share the same final velocity. Does that make sense? All right, what's the initial momentum of block 2, of object 2? 0, that goes away. So what we're looking for is V1 initial. So V1 initial is going to be M1 plus M2 times V final divided by M1, okay? So what's our challenge now? We need to figure out V final. We need to figure out what is the velocity immediately after the collision. Well, do we have some more data here? We have the height of the table. The height of the table is 1 meter. And then we also have the horizontal displacement when the bullet block combo leaves the table. Does that make sense? So can we figure out what velocity the bullet block combo has as it leaves the table? We sure can. What are we going to use? What does this look like right here? Projectile motion. Okay, so look, we only have a few minutes, so I'm not going to go in super detail about projectile motion. If you're like, whoa, dude, I forgot projectile motion, you can go back and watch one of the many videos from projectile motion. But you're going to have to know it, because at the end of chapter 7, what's waiting for you? The midterm. You got to be good at all aspects of physics. Okay, so for projectile motion, one of the key things is that you got to break x and y apart. As the block flies through the air, what's the x acceleration? 0. What's the y acceleration? Gravity, right? Why is the x acceleration 0? Because the x velocity stays what? Constant. All right, this 2 meter right here is our x displacement. This 1 meter is the y displacement, and that's negative. Why is that going to be negative 1? Well, does the block go up 1 meter or down 1 meter? It goes down 1 meter, so that's negative 1. Okay, so what we're going to do is we're going to first find the time in the air using the y direction. So using the first kinematic, we go y equals 1/2 gt squared plus vy initial t. What's the starting y velocity as the block leaves the table? It's 0. There is no y velocity when the block leaves the table. Because why? The velocity is all in the x. As it leaves the table, it's perfectly x. Okay, so now you go t, we're solving for time. That's going to be 2y over g square rooted. So 2 times negative 1 over negative 9.8. This gives a time of 0.4518. Okay, so now we have the time in the air. So now that we have time, oh man, hold on, I'm almost done. So now that we got time in the air, just pack up quietly so I can just finish this. Okay, so now we go to the x direction and we find Vx. So there's only one x equation, x equals Vxt. So Vx is going to be x over t. The x is 2 meters. We now have the time. So now this is 4.427 meter per second. That is this. So you plug that in up there. The initial velocity of the bullet, when you plug it all in, comes out to be about 142.8.